All right, welcome to the Explainer. Today, we're going to break down a concept that's basically the silent guardian of our entire digital world. I'm talking about everything from bank transfers to your online shopping cart, the database transaction. Now, I know it sounds super technical, but I promise you, it's way more intuitive than you think. So let's dive right in.
Okay, to really get why transactions are such a big deal, let's start with a really simple question. Imagine you got two kids, and they share one single piggy bank. Now, one of them wants to put $1 in, and at the exact same second, the other one wants to take $1 out. What happens?
Yeah, exactly. It gets messy. The final amount is almost definitely going to be wrong. Maybe the dollar coming out doesn't get recorded right because the other one was going in. The piggy bank, our database, just gets confused, and the balance is totally wrong. That's the core of it. This is the fundamental problem of concurrency. Just lots of things trying to happen all at once.
So, how do we fix this? Well, we bring in this really powerful rule called a transaction. Think of it like a strict parent telling the piggy bank, listen up, you are only allowed to do one complete action at a time. And if any little part of that action fails for any reason, you have to hit the undo button on the whole thing and pretend it never even started. It's a true all-or-nothing deal.
Okay, so how do we actually make this all-or-nothing rule work in the real world? Well, databases give us a pretty simple but super powerful rulebook with just 3 key commands.
First up, you tell the database begin. That's like saying, hey, start paying attention. Everything I do from now on is one big group. Then, once all your steps are done and everything looks good, you say commit. That makes all the changes permanent, set in stone. But if anything goes sideways, you shout rollback, and poof, the database instantly undoes everything back to the moment you said begin.
And that right there is the simple, beautiful promise. When you're moving money, it's not one thing, right? It's 2. You withdraw from one account and you deposit into another. The transaction wraps those 2 things together and guarantees, absolutely guarantees, that either the money makes the full journey or it never leaves the starting account. Nothing ever gets lost in limbo.
So, transactions solve our piggy bank problem. We're totally safe now, right? Well, not quite. See, when you've got thousands of these transactions all running at the same time, some really bizarre, spooky things can start to happen. I like to call them ghosts in the machine. So let's meet our first ghost, the dirty read. This is a nasty one. It happens when one transaction is allowed to see the messy, half-finished work of another transaction, work that hasn't been saved yet and, more importantly, might just vanish into thin air.
Just picture this. Transaction 1 goes in and updates a bank balance. But before it hits commit, transaction 2 sneaks in and reads that brand new temporary balance. And then, transaction 1 hits an error and has to roll back, completely undoing its change. And the result? It's kinda terrifying. Transaction 2 is now operating with information that was never officially real. It literally saw a ghost. And making decisions based on data that never truly existed, that is how you get some really bad system-breaking bugs.
All right, on to our next ghost, the non-repeatable read. This is when you ask for the same piece of information twice inside your own single transaction, but you get a different answer each time. It feels like the world is changing right underneath your feet while you're trying to work.
So here's the play-by-play. Your transaction reads the price of a product. Let's say it's $10. In that tiny sliver of time, another transaction comes in, changes the price to $12, and successfully commits it. A few moments later, your first transaction asks for the exact same product's price again.
And just like that, boom, same question, different answer. If your transaction was in the middle of calculating a total or checking a budget, its entire logic is now completely busted. The consistency that you were counting on is just gone.
And that brings us to our last, and maybe the sneakiest ghost of all, the phantom read. This is a lot like the last one, but instead of one value changing, entire new rows of data just appear out of nowhere when you ask the same question twice.
So, for example, your transaction asks the database, show me all sales over $1,000, because you need to calculate a total commission. While you're doing that math, another transaction zips in, adds a brand new $2,000 sale and commits it. Now your transaction runs its query again, maybe just to double-check the final number.
And suddenly, a phantom row has just appeared. A whole new sale that didn't exist a millisecond ago is now in your results, throwing your whole calculation off. It's as if a ghost just materialized right inside your data.
So, how in the world do we fight these ghosts? This is where we get to fight back.
Databases give us the power to choose our level of safety, or what's called isolation. We can literally tell the database which ghosts we're okay with and which ones we want to banish completely.
And there are 4 standard levels, kind of like security settings. You've got read uncommitted, which is basically the Wild West. All the ghosts are allowed. Then there's read committed, which is a pretty common starting point. Repeatable read locks things down even more. And finally, you have serializable. That's Fort Knox, maximum security.
And this table right here, this is our ghost hunting cheat sheet. It lays it all out. You can see that read committed takes care of those nasty, dirty reads. Step up to repeatable read, and you're protected from non-repeatable reads too. And if you go all the way to serializable, you're safe from everything, including phantoms. But here's the critical takeaway. It's a trade-off. More safety can mean less speed, so you have to consciously pick the right balance for what you're trying to do.
Now, you might be wondering, how does a database actually do all this? It's not magic, right? Well, no. It mostly comes down to a clever idea called locking, and a couple of different strategies on how and when to use those locks.
So you've basically got 2 main philosophies here, pessimistic and optimistic. The pessimistic approach assumes that conflicts are going to happen all the time. So it's cautious, it locks the data it needs right at the beginning, telling everyone else hands off. It's super safe, but it can slow things down. The optimistic approach assumes conflicts are rare. It just goes ahead and does its work without any locks, but then right at the very end, it does a quick check to see if anyone else changed the data. If not, great. If so, it has to roll back and try again.
Okay, so now that we've got all the theory down, let's get practical. Here are the key rules you'll want to live by when you're actually designing systems with transactions.
Rule number 1, keep your transactions as short and as fast as you possibly can. A long-running transaction is like blocking a 1-lane road. Second, and this one is a huge deal, never, ever wait for a human to type something or for a slow network call to finish while you have an open transaction. Third, don't just accept the default isolation level. Think about what you need and choose it on purpose. And finally, always plan for things to fail. Design your code so it knows how to retry a transaction if it gets rolled back because of a conflict.
And really, that brings us to the core of it all. The problems that concurrency causes, those ghosts we talked about, are sneaky. They can creep in and corrupt your data silently over months or years. Transactions are the exact opposite. They are a loud, clear, and totally enforceable promise that your data will stay correct and consistent, no matter how much chaos is happening around it.